afternoon, teacher.
Good afternoon, teacher.
Last time we had introduced thermalconductivity, and we have seen the rate at which heat is lost, the surrounding. We did most of the derivations, and we promised ourselves to have the calculations this lesson. So we are expected to see some of those numbers and how we can always go about them. So a quick reminder of what transpired last week was we had seen how the rate of heat transfer, or the rate at which heat is transferred, can be interpreted. So we are looking at thermal conductivity. Thermal conductivity or coefficient of thermal conductivity. And we had realized that the rate at which heat flows is given by the thermal conductivity K of a given material times the cross-sectional area times the temperature gradient, whereby the temperature gradient is the difference in the temperature at the ends of the conductor and the length of the conductor. So if you recall, we saw K as the constant called the coefficient of thermal conductivity. This was our coefficient of thermal conductivity. Then we had the cross-section area. Then we had θ1 minus θ2 out of L as the temperature what? Temperature gradient. So you can take a look at examples, calculations on this, and we see how we can go about them. So we can have an example here. Example 1. We have a copper rod. Copper rod, 2 meters long of diameter, 3 centimeters, is lagged. One end is kept at 300 degrees Celsius, and the other end is pressed against a 2 centimeter thick cardboard disc. Cardboard disc of the same diameter. The same diameter as the rod. A free end of the disc is maintained at 40 degrees Celsius. If the thermalconductivities of copper and cardboard are 380 and 0.2 watts per meter per Kelvin, respectively. Calculate 1. The steady state temperature at the copper cardboard junction. Then 2, the quantity of heat flowing across the junction, 10 minutes. So we have a copper rod of 2 meters long, of diameter 3 centimeters, that is lagged. One end is kept at 300 degrees Celsius and the other end is pressed against a 2 centimeter thick cardboard disc of the same diameter as the rod. The free end of the disc is maintained at 40 degrees Celsius. The thermoconductivity is at that, calculate the steady temperature at the junction. Now, first of all, I can assume this is the copper rod. And I can assume this is the added on what? Cardboard. Having the same thickness as the copper rod. But this is copper. This is our cardboard. Whereby the thermoconductivity of copper, case C, is 380 watts per meter per Kelvin. The thermoconductivity of the cardboard is 0.2 watts per meter per Kelvin. This is 2 meters long. Whereas this one is 2 centimeters. They say it is. It should have been 2 centimeters long. It's pressed against a 2 centimeter long cardboard disc of the same diameter. So if it has the same diameter, then the thickness is the same. So this should have been 2 centimeters long cardboard. So this is 2 centimeters. So this side is maintained at what degrees? This side is maintained at 300 degrees Celsius. Whereas the cardboard, this side is maintained at how many degrees? 40 degrees Celsius. So it is from here that we can look at the rate of heat transfer, which is 2 out of T, given by Ka times the temperature difference. This is temperature theta 1. This one can be temperature theta 2. They're asking us to look for temperature at the junction. Temperature at the junction can be theta 3, which we don't know. Or it can be theta, any value you want. Now, with that, for copper, only, the rate of heat flow will be equal to the coefficient of copper times the cross-sectional area times 300 minus temperature θ3 out of the length of copper, which length of copper was 2 meters. So this can be equation 1. For the cardboard, the rate at which heat flows is going to be 0.2, the coefficient of the cardboard, times cross-sectional area, times this temperature definitely will be greater than the temperature at the extreme, so θ3 minus 40, divided by 2 times 10 to the power negative 2. This is equation 2. Now, for steady state, the rate of heat flow is a what? Is a constant. And therefore, the rate at which heat flows in the cardboard is going to be equal to the rate at which heat flows in the cardboard is equal to the rate at which heat flows in copper. So if they are the same, you can equate, because the diameter was the same, the cross-section area was the same. Cynthia, you have a hand?
If I want to ask,
Yes, please.
how do you know it's divided by 2 times 10 to the power negative 2?
Okay, I had identified them here. Eh? The length of copper was 2 meters. The length of the cardboard was 2 centimeters. So 2 times 10 power negative 2 meters. Okay. Then the temperature this way, because this one was at a low temperature, this temperature θ3 at the end of the cardboard here, the cardboard would have gained heat. So when it gains heat, θ3 is greater than 40. That's why I'm saying θ3 minus 40. Whereas for the copper here, the copper has an extreme of 300. It is going to lose heat to the cardboard. So θ3 will be at a lower temperature than the other extreme end with 300. So therefore, we shall have 380 times cross-sectional area divided by 2 into 300 minus θ3 is going to give us 0.2 times cross-sectional area of θ3 minus 40 divided by 2 times 10 power negative 2. I can lose the cross-section area by division. I can lose this 2 by division as well. So I'll have 380 into 300 minus θ3 is equal to the negative 10 power negative 2 can go up to give us 20. So it will give us 20 into θ3 minus 40. Can you multiply 380 times 300? What do you get? That is 76 plus 38. That is 109. 109. So 1,000.
114,000.
1?
114,000. 114,000.
114,000 minus 380 θ3. You could have even reduced it from there. Is equal to 20 θ3 minus 800. So when I combine the two, I'll get 400 θ3 is equal to 114,800. So I can divide both by 400 by 400. What is θ3? We're dividing θ3 by getting 148 divided by 4, which gives us a 2, remainder 3, because there are 8.
287.
287 degrees Celsius. And indeed, the temperature there should be lying between 300 and 40. So it is between 300 and 40. If you get a temperature which is greater than 300, yet it is at the junction, which one junction brings a lower temperature and the other brings a higher temperature, Then you check your algebra again. So you can have that down. Let me use this small space here. The question has gone ahead and said, the quantity of heat flowing across the junction in 10 minutes. So we have seen that Q out of T is equal to Ka into 300 minus theta 3 out of L. You can use any. So you make Q the subject, which will be 380 times the cross-section area, which is going to be 22 out of 7 times 1.5 times 10 power negative 2 squared, that is the radius squared, into 300 minus 287 divided by the length, of the copper, which is 2 meters, times the time, which is 10 times 60 seconds. With this, you can get the quantity of heat. You're going to investigate whether when you use the cardboard, you still get the same answer.
1047.99.
It should be 0.56, joules. Then I want you to investigate, what if we use this second one? We get the same answer? Investigate the second one and see whether we get the same answer. Otherwise, any issues should give you the same answer. Then the exercise I will leave, the number I will leave for assignment, I will expect people to present it and send it out to me on the group so that I can take a look at it. You can inbox me the solution. There's a number I want to give you, which will be having 3 items. Hope you've taken the screenshot. I want you to try out that one as I write down the number. Can I flip the page? Also, the number I'm going to write here, I've sent it on the group, plus the assignment you're going to handle. So
2.
Any solution to the answer of what I've asked you to investigate?
I've gotten 149.576.
Are you sure? You get a different answer. Should be the same answer. Anyone else who has got the same answer or a different answer, slightly?
Please go back to the previous screen.
Okay. Anyone who has got the same answer as we got? Or we all have different answers? I expected the answers to be the same, guys.
I have 1,047.99.
0.99, eh? Even the first one was the same,
Yes.
eh?
Yes, it was 0.99.
Oh, okay. Okay, then, so what I wanted to show you out of that is that if you use the one for the cardboard, don't worry that you'll get a wrong quantity of heat. You can as well use the one for the cardboard, you can as well use the one for the copper rod. Okay. Let's have someone read for us this question. Madina Tasnim. Madina, you sound to be new. I've not heard of you before. Madina.
Yeah.
You're new?
Yeah, I'm new.
You're welcome. Now you'll go and check my YouTube channel. It's Wama Hamza, and check for some of the lessons we've already covered. Okay?
Okay.
Yeah.
Yeah.
So read this question.
A well-lagged composite metal bar of uniform cross-section 2 centimeters squared is made, joining a 40 centimeter rod of copper to a 25 centimeter rod of aluminium. The extreme ends of the bar are maintained respectively at 100 degrees Celsius and 0 degrees Celsius. Calculate the temperature of the junction of the two bars and to the heat flowing through each bar in 5 minutes.
Okay, so this is how the bar looks like. The bar is made by joining copper and aluminium of cross-section area, 25 centimeters squared, and the copper is 40 centimeters, whereas the aluminium is 25 centimeters. Now with this, we shall need to get copper. The rate of heat flow through copper is going to be the temperature coefficient of copper, thermal conductivity of copper, times the cross-section area, times the temperature difference, which is going to be 100 minus theta, divided by the length of copper. This will be 2 for copper out of T is going to be equal to, copper is 386 times cross-section area times 100 minus the unknown temperature divided by 40 times 10 power negative 2. This will give us equation 1. Then for aluminium, the rate of heat flow through aluminium will give me the thermal conductivity of aluminium times the cross-section area, which is the same, times theta minus 0 degrees out of the length of aluminium, which is 25 times 10 power negative 2. But for steady flow, the rate of heat flow is the same. Therefore, the heat flowing through copper per second is equal to the heat flowing through aluminium per second. So with this, we shall have 386 A into 100 minus theta divided by 40 times 10 power negative 2 is equal to 210 times A into theta divided by 25 times 10 power negative 2. When you simplify, we shall realize this is lost with that. Yeah. Then by 4, 10, sorry. Okay, let's cross multiply straight away. Don't need to divide by 4. Let's leave this out. So I can lose the A by division. Then I'll realize 386 times 25 into 100 minus theta is equal to 210 times 40 theta. So 210 times 40 is 21 times 4, which is 84, which is 8400. Theta is going to be equal to 25 times 386. What do you get when you multiply 25 times 386?
9,650.
9,600. 50 times 100, you add on 00. So therefore, I'll have 8, 7, 8, 6 theta is equal to 965,000 divided by 8786 divided by 8786. What is the value of temperature theta at the junction?
109.8.
What? 100?
109.8.
Wow,
Yes.
that is impossible. I told you the temperature cannot be beyond the highest.
Teacher,
Yes?
I think you made a mistake on the temperature. 386 times 25 times negative theta doesn't give 386 theta. It gives
Oh,
1,000.
thank you so much. Yes. It gives us
18050.
this one, eh? 18,
050.
like that, eh?
Yes.
18,000. 18,000 plus 8,000, we get 26,050. True? 26,450. Sorry, I missed the multiplication of 25 with this to confirm the theta. So it's equal to 965,000. That's why I said, whenever you get a value of temperature, for example, here you get a negative temperature, stop working. You get a temperature beyond 100, check yourself. What is theta? I think now it's okay.
Theta is 36.48.
Is that so?
Yes.
Okay, so that's better. So we can as well go ahead and find the quantity of heat. I can use the one for aluminium, which is coefficient of aluminium, cross-section area times theta minus 0 divided by the length of aluminium. The quantity of heat would be, in 5 minutes, would be 210 times the cross-section area is 2 times 10 to the power negative 4, because you convert it to meters, times 36.48, all is divided by the length of aluminium is 25 times 10 to the power negative 2. Then times 5 here, times 60. So what is the quantity of heat? Remember, we have to investigate also and see whether copper gives us the same. So you're going to check it out using copper.
Okay, so the topic is cell division. Cell division. Yes.
1,838.592.
Cell division.
Point?
Now.
0.592.
What?
592.
But is that temperature okay? Looks like I have a different value. Does someone have a different value? Anyone with a slightly different value for the temperature? Yeah? Hmm?
It's the same.
The same, eh? Okay. Let's go by that.
So I think there's a problem.
Where?
386 times 25 gives
386 times 25 gives?
9,650
10 times 100.
on theta. 386
Hey.
times 25 times negative theta.
386. Now, who gave us 18? I think the 18 multiplied by 2. Someone who gave us 18 gave us something different because the theta is 53.46. So I can see if you change that. So you're saying it's what? When it moves, it is a negative, but when it moves over, it becomes a positive. Eh? You're saying it's 9,650, isn't it? Is that what you're saying? Yeah. Okay, then that's why we have to be patient on the calc. Then 9,650 plus 8,400. The answer you get there is what? 17,000. You get 18,050.
Yes.
18,050 theta. Divide by 18,050. Divide by 18,050. When you press the calc, what answer do we get?
Yeah,
53.4626.
53.
Yes.
Yeah, that is the correct answer. So they are not so complicated, but the algebra here of substitution, dividing, cross multiplying is the problem. That's why we have to be more patient on this. So this becomes 53.46. So what answer do we get here now?
$2,694.5152.
Okay. Now try the same using copper. And we confirm whether we have the same answer.
Two 2,694.67.
0.67. It's a slight deviation, okay.
Yes.
But still we get almost the same answer. So 2,694.67. So whether you use the one for the copper or the one for the aluminium, all rods should give you the same quantities of heat as far as heat flowing through the entire bar is concerned. Now I've given you a number there, which is talking about a composite bar, but let me give you a hint on it. It's made of aluminium, copper, and brass. The rods which have equal length and diameter are placed end to end and lagged as shown. So they are lagged in a system like this one. So if they're lagged in a system like that one, we have this as copper. Maybe this one can be for aluminium, then brass. So we have aluminium and we have brass. But it is lagged. So if it is lagged, this side is 100, this way is 0. The ends of the composite rods are maintained at 100 and 0. Given that coefficients of copper to coefficients of aluminium to coefficients of brass, they're in the ratio 18 to 10 to 5. Yeah, determine the equilibrium temperature at copper, aluminium, and aluminium brass junctions. So they want the temperature here, theta 1. They want the temperature here, theta 2. Right? These ones have equal length, so all this is L, L, L. I don't want to do the number, but you go ahead and use the equation. For heat flow, they should be the same throughout the entire system. So for copper times cross-section area of copper times 100 minus theta 1 out of the length L should be equal to the coefficient for aluminium times cross-section area times theta 1 minus theta 2 divided by the length should be the same as for brass times cross-section area for brass times theta 2 minus 0 divided by the length L. Then use your knowledge of mathematics and express them in terms of the same thing. Then the coefficients will cancel. Then you solve by designing a simultaneous equation, and then you attain the solution. So I've almost solved the number by 3/4. Yeah? So please try out that number. It's very interesting to look at. Then there is another Y junction. I'll bring it next time after we have discussed the experiments. Unless if someone has a question, but our time is up. So please finish that number I've sent in the group. For that, I will need to take a look at your answers. Otherwise, if no further questions, please endeavor to try out some of those numbers. The new lady, please visit the YouTube channel for more lessons that you have missed. Okay. With that, have a nice day.